Having already examined the layout of the ED6 VFR chart, we shall now use this chart to plan a simple VFR route. In addition to the chart, you will need your plotting instruments, pencil, navigation ruler, dividers, protractor, and lastly, a VFR flight log. However, the VFR flight log is not really necessary to have, as an example one will be used in the lesson. An example of a VFR flight log is shown here. There are many versions, but this one contains the most important elements and therefore can be used as an example. Once completed, the flight log forms a very important part of the flight. At each break pause or break point in the lesson, complete the instructions you have been given before moving on. The route is from overhead Bad Waldsee to overhead Gunzenhausen, so locate the position of the departure and destination airfields from the aerodrome section on the back panel. Identify them on the chart and draw a line between them. Now that the route is drawn on the chart, we can measure the track angle. This is a Lambert's projection, where straight lines represent great circles. Therefore, to measure the mean track, place the protractor near the centre of the track as shown. Then align it with the nearest meridian and read off the true track angle. You should have measured an angle of 030 degrees true. This value must be entered in the appropriate column of the VFR flight log, as shown. You will be using a magnetic compass in the aircraft to actually fly this route, so we need to determine variation so that we can use a magnetic heading and magnetic track. Variation is shown on charts by isogonals, but these can be difficult to find on this chart. An example of one is shown on screen, which is just to the right-hand side of Zurich. The line shown is the 0 degree isogonal and is a black pecked line. If you can't find an isogonal, you can use the variation of nearby navigation aids. In this case, use Lorpheim and Nordlingen. The information on the back panel shows that the variation at Lorpheim is 0, and the variation at Nordlingen is 1 degree west. For demonstration, we shall use Nordlingen. Using the rule you learned in navigation, variation west, magnetic best, we can say that since the true track is 030, the magnetic track must be 031 degrees. Enter 031 in the appropriate column of the flight log. The scale of this chart is closer to 1 in 515,000 rather than 1 in 500,000. So for accuracy, measure track distances using dividers rather than the navigation ruler. Open the dividers to a convenient distance, say 30 nautical miles, on the nautical miles scale at the bottom of the chart, or 30 minutes of latitude from 48 degrees north to 48.5 degrees north along a line of longitude. This is because the chart scale is accurate at 48 north, and therefore 30 minutes of latitude is 30 nautical miles. Take the dividers, being careful not to change the distance, and start measuring along the track line you have drawn by marking 30 nautical mile arcs. On the last part of the track, adjust the dividers to measure the remaining distance. Then, take that measurement to the scale at the bottom of the chart. It should show a distance of 23 nautical miles. So in total, you have done 2 sections of 30 nautical miles and 1 section of 23 nautical miles, giving a total track distance of 83 nautical miles. Enter this in the flight log. In the next section, we will examine the safety altitude. The safety altitude is calculated to ensure we have an adequate safety margin above the highest terrain either side of the track. It will indicate the lowest safe altitude we can use along the track. In order to calculate the safety altitude, we find the highest obstacle on the chart within 5 nautical miles either side of the track. Draw a line 5 nautical miles each side of track and an arc 5 nautical miles radius around each end of the track and find, by inspection, the highest obstacle within the defined area. By inspection of this area, you should see that the highest obstacle is a lighted tower 5 nautical miles southeast of Nordlingen NDB. The height of the tower is 2,377 feet above mean sea level. This is indicated by the fact that the figures are not in brackets. The rule for calculating safety altitude is to first round up the figure to the next 100 feet. Then, if the figure is 5,000 feet or less, add 1,000 feet. But if the figure is 5,001 feet or more, add 2,000 feet. The resultant is the safety altitude. In our case, the safety altitude is 3,400 feet, which is written in the flight log. In the next scene, we will discuss another minimum safe altitude factor, called a minimum grid area altitude. The minimum grid area altitude, also known as the minimum off-route altitude, MORA, can be found directly from the chart and entered in the flight log. You will notice some big red crosses around the area of the planned route. Inside these rectangular areas are some large red numbers as shown. The large figure indicates thousands of feet and the smaller one hundreds of feet. These values are the minimum grid area altitudes. In this example, it is 4,300 feet. Looking at the rectangles that affect our route, you will see that the highest minimum grid area altitude is in the rectangle from which we are leaving, which is shown as 5,900 feet. As a rule, always select the highest value that affects the entire route, which in our case is 5,900 feet. With experience and for practical purposes, it could be argued that this is actually behind the route, and therefore we could use 4,300 feet. However, for the purposes of this exercise and the examination, use the highest level, which in this case is 5,900 feet. The minimum grid area altitude is used slightly differently from the safety altitude discussed previously. If you become lost or lose sight of the ground, then it is the minimum grid area altitude that is the lowest altitude at which to fly. This gives the greatest possible protection against terrain in the area in which you are flying. Don't forget to add the minimum grid area altitude to the flight log. Before deciding which altitude or level to fly, it is necessary to find what restrictions or hazards lie along the route. The first restriction is the airspace around Lorpheim. This is Class D airspace up to 3,500 feet and will require prior permission before entering it. Numerous glider sites and small airfields are on both sides of the planned track, and this requires a good lookout to avoid any conflict. And of course, there is the tower, which rises to 2,377 feet above mean sea level. If you stay above your safety altitude, then such obstacles do not present a problem. By using the Flight Information and Meteorological Services diagram at the bottom of the chart, the frequencies for the appropriate services can be found. Transpose the route to the diagram to determine the frequencies for FIS and MET. We can now choose an altitude or level to fly. Above the transition altitude, pilots must fly on flight levels and comply with the semicircular rule which is shown on the screen. This is shown diagrammatically at the bottom of the map. It can be seen from the diagram that a magnetic track of 031 degrees uses the flight levels on the right-hand side as highlighted. Flying too high for our type of flight is inappropriate, so really the only flight levels worth considering are flight level 35, flight level 55, and lastly, flight level 75. However, the transition altitude in Germany is 5,000 feet, which means we do not fly at flight levels below that altitude. Therefore, flight level 35 can't be used. As the transition level is 60, flight level 55 can't be used, as it sits inside the transition layer within which level flight is not possible. Therefore, if you want to fly flight levels, then flight level 75 seems the most obvious. And since it is above our safety altitude of 3,400 feet, it would seem to be the sensible choice if you are able to climb that high. Below the transition altitude of 5,000 feet, the semicircular rules do not apply. Therefore, we could fly at any altitude below 5,000 feet, but above our safety altitude of 3,400 feet. Just be careful of entering the Class D airspace up to 3,500 feet around Lorpheim unless you have permission. A few assumptions have been made in the choice of your altitude with regard to the semicircular rule, the transition altitude, and so on. Do not worry, as these concepts will become clearer as you work through the other parts of the training course. It is part of the chart preparation to pre-plan some significant pinpoints and fixing aids. These can be highlighted on the map before flight. The loop in the railway south of Lorpheim, the railway and river east of Ulm as an ETA check, a beam Nordlingen NDB with the tower to the right of track. Gunzenhausen can be identified by the town on the lake to the northwest and the railway junction to the west. The main chart work is now finished. However, the planning of the flight is actually not complete. The instruction you need in order to do this will be taught and covered in other areas of the syllabus. So, to conclude, and to complete the exercise, obtain the weather information and using the CRP5 calculate the heading to fly, ground speed and ETA and complete the flight log.